speaker of today, Vahid.
Yeah.
Go ahead.
Okay, thank you. Thank you very much, everybody. First I want to thank the organizer, Pierre, Alex, who I met actually at the Fields Institute. I know them because we were here in 2014 at the time in the series of workshops for big data for about a month. And we became friends, and now they invited me to give this talk. I tried to say no, but at the end I couldn't. So I came here and gave a talk last minute. I'm sorry, I'm preparing my talk last minute too. So, let me talk about large language models a bit. I have a confused feeling myself. So some people like it, some people dislike it. So I'm one of the people who disliked it in the beginning, and I'll start getting more and more curious through time. So maybe in the introduction section, I give you a brief history about my nonlinear career. That in 2012, I started before I was a postdoc at McGill and at Stanford in statistics, and then I became like a faculty at 2012. Then I left to Huawei. I wanted to collaborate with them, but later on I ended up joining them. They were more flexible than academia. So, and I was lucky to be in a group that I had the flexibility of choosing different teams. I started with decision-making and reasoning lab, and then I went to the computer vision lab where the deep learning started, and then now I'm in the speech and semantics lab where the large language models are developed. Still, I keep my NSERC Discover grant. Still, I have graduate students in academia and spend some time, about 1 or 2 days at my university office. And meanwhile, and I feel that I have still a bit of time, I teach at McGill, but not in the math department. Well, I'm a mathematician by training, but I teach at electrical and computer engineering department, usually in the fall. 1 course only. Okay, so I'm lucky to hear from Jun Hao, my intern from U of T, who joined us actually in the summer, that actually the JASA, Journal of American Statistical Association, has a special issue on AI, and it's very rare. You can consider that as like equivalent of Annals of Mathematics, that doesn't require a special issue, but suddenly they decided to give a special issue. I think that's an important topic. Now, AI, I think for the future of our students to learn the capacities required in the industry to contribute in the society more. We are in a direction that AI is going to play a major role in our future. Not even us, I mean, of course we're going to see that, but for our kids even more interesting. So we need to train ourselves. So let me start with large language models. They are getting bigger and bigger through time. The first, called large, was the BERT model, that the large BERT was 340, if I'm not mistaken, million parameters. Now even they call nano 2.8 billion is the nano model. And you can easily think about 2 trillion model as a large language model. And you start thinking, why? Why the language models are getting larger and larger through time? And there is a reason behind that. There is a scaling law. So the first paper by Kaplan, this is the same people of OpenAI, showing that you can get a better prediction of words at this stage. So transformer type models. These are the ones that ChatGPT start using. You just, more parameters, more words, more text, feeding them means a better loss. So that's the first message. The second message was that you don't need to train large models. You can train small models and predict what's going to happen if you increase the number of parameters. And it's pretty much architecture dependent. So you want to take GPT, you want to get BERT, as long as it's like transformer type models, you don't care. So it seems that the architecture doesn't matter. People start maybe Chinchilla, I don't know, whatever other models that other companies are presenting. The scaling law says they don't matter. You just increase number of parameters, you increase the number of text you're feeding to your neural networks, you're going to be fine. So there is like computationally intensive algorithms required, or maybe hardware required, to run these models at the end and provide this like product to people. And the second paper that was like more recent, saying that actually most of the neural networks that you're seeing in large language models are undertrained, in the sense that they have more parameters, but fewer words feeding them. You don't don't need to increase the number of parameters, just increase the number of words, and almost 4 times more, that's okay. Then you start getting the maximum of the parameters that you add. You add more parameters, you feed more data, 4 times more, and you will be fine. You can use a better model. You have a better prediction model by these scaling laws. So these are the 2, I think, main messages that we've got from these studies. Now, we go to real computation. So maybe many of you know that we compute on float 32. And there's a reason behind that. There has been a standard, IEEE standard, so most of the physical constant can be represented in FP32 format, but not in the other ones necessarily. So the scientific computing is based on actually scientific consensus of what will be the right floating point, how many exponent bit, how many mantissa bit we put, and then we start putting algorithms behind, linear algebra behind these number formats. And sometimes I ask this question to my interns that, why do you think real numbers are necessary? Because at the end, we're going to simulate on FP32. And these are not even rational numbers. There's very small subset of rational numbers. So what would be the point of even studying real numbers? Okay, we can think about that. Or what does this simulation mean? Because they don't represent real numbers at all. Okay? So let's think about that. Because the epsilon of that computation is so low, maybe you consider it's a good approximation of real numbers. But the real computations that are running now on the cloud that's serving us ChatGPT or whatever are FP16 in the best case scenario. So you start feeling the epsilon. And hardware that are coming, computational hardware that are coming, I mean, more recently, the advantage is that they go to even harsh, lower bit numbers. So we can think about like that. I compute on FP32 because the computation is meaningful. They have a certain meaning. They compute a certain model that are important, and we understand them. But when you go to deep learning, it doesn't really matter, does it? They just need to compute, and even it's stochastic. So you don't need to compute precise. So why you don't go to lower bits? Okay. So that says perhaps the computation engine that you need for deep learning would have been different from the one that you use mostly for scientific computing. You just don't need that precision anymore. Okay. Let's talk about NVIDIA now. We have H100 out. A100, the advantage is that it uses like integer 8. And you can go to FP8 now. That means certain mantissa set. I don't know if you guys are aware of mantissa exponent. No? Okay, so that's something that's missing. I think for people who have a programming language, first, we need to, I think, teach them number format as well. We just don't know the behavior of number format. That governs everything. Actually, your algorithm will be run on the number format at the end. So you don't know how they behave. We think that it's going to be all right. We trust our engineers at the end, and we may not. Okay, so as time goes, it becomes lower and lower bits, so it's not going to work. We must understand what's going on in the number format, and sometimes even hardware. So I give you an example that I didn't understand the hardware actually was difficult to implement. Certain algorithms are actually meaningless. So Peter asked me if you can, Pierre asked me if you can put this on the context of finance or complex networks. So that's, I think, I would say. Bloomberg GPT came out maybe I think a year ago or maybe more. And then they spent like 30 million to bring the open chat GPT type from the Bloomberg data. And I think a few months after, a guy fine-tuned a model with less than $1,000 and surpassed Bloomberg GPT. Okay. So financially, if you're thinking about running a big company, replacing some individuals or making more efficient by putting a certain conversational agent behind, then you may start thinking that you need to know about large language models as well, because they're going to govern at the end the interaction between people, or maybe between the customers and the institution. So like Public Mobile, the cell phone company of TELUS, doesn't have any people for customer service. Everything is fully online. And the chat is fully executed by a language model. So it's actually a virtual company now. So what happens in the steps of pre-training of a large language model? I'm not sure that I need to go into that details, but because Bloomberg GPT's story is interesting, maybe we have a pre-training stage in which the pre-training part is composed of giving the words before, predicting the word after. That's pretty much it. So give the history, predict what's the next word. It's not an easy task even for a human. Okay? These are like generative models. There are non-generative models like BERT. That means fill in the blank. You give before and after, you ask to fill in the blank. That becomes non-generative large language models. Most of the models now are generative. So are pre-trained like sequence of words before given to the model, just predicts the next word. And given the new window, predict the next word. That's how you pre-train. And people start thinking that pre-training is quite an important phase, because even if I'm interested in a simple task like, is it a positive comment or a negative comment that doesn't require understanding the language? This step is actually understanding the grammar and the context and the language. And the next step, which is fine-tuning for a certain task, like is this positive, is this comment positive or negative, becomes easier for the model. So we learn through time that pre-training then fine-tuning always somehow surpasses training for that task. We learn something else too. We train a larger model, then we train a smaller model that mimics the larger model, always have a better accuracy than training that small model from scratch. So that's why we are interested also in large language models. We can do better, we can predict better, and hopefully if it's in the human level, then we can remove humans from the conversation and the machine takes over. And there is something else also you need to consider, that this has been before OpenAI as well, before ChatGPT. What changes the story is about human feedback. It's trained with human feedback. So there was a reinforcement learning engine that also fine-tuned this model, not only based on the text, but how we prefer to see the answer. And now it's happening as like generating codes right now, so pretty much we don't need that much people to code, because we can ask Copilot to write for us, okay? So what we learned from Bloomberg story is that you just don't fine-tune, because you get a pre-trained model, you start changing these weights, neural network weights. Perhaps the right way is just keeping that weight, modifying it, delta W, and just fine-tune that delta W, because the original weight is going to stay there. You don't lose the performance and understanding of a language. You just learn the delta W, and it's quite low-rank version. Low-rank version because you just have fewer parameters there. If you make a low-rank structure. So you don't train the weights, you train the weights that you get from pre-train plus the delta W. And at the time I started thinking that, why low rank? When the models gets large, we have something that makes the models large, and it's not a matrix product. So all neural networks are true matrix product. The Kronecker product expands. So perhaps that's the right tool. So I get back to this later. How much time do I have?
5 minutes.
5 minutes? Okay. So let me maybe jump from the details, saying that if you start training a model in a high precision and low precision, something that we lack in theory is that the number format is missing in our theory. What does it mean when we talk about convergence rates, we talk about on real lines. We know that we are not going to run them on real lines. So the question that the right question to ask is that, what happens to the convergence when we run it in lower bit number format? And pretty much we started learning that about 3 years ago, starting understanding this a bit further and seeing that, well, the traditional SGD can be extended so that the number format also comes in. And there's another part is that when you start learning a manifold, I mean, estimating the parameters to learn a manifold, going from floating point 32 to integer 8 doesn't change a lot, but go to int 4 seems impossible. And you see weekly, I mean, the result is much different. So it's not very surprising to see that maybe it was a wise decision at the time that Commodore 64 was 8-bit. We had the 8-bit engine because it seems that the floating point 32 computation, at least in the neural networks type, is very similar, and you don't need to go to higher bits. And if you go to int 4, they're going to diverge. So let me just bring this part out, that if there is something, I think, in the future of neural networks to be considered as a development, is to replace the matrix product with Kronecker product. They are expansive. So when you multiply them, they're going to expand, and maybe the large language model is only coming by this Kronecker product. And the interesting part is that you don't need to expand first and do the matrix multiplication. There is a way of bringing it already in by, if you have like A times B by X, then you can reorder them and do the matrix product. You don't need to expand the matrix because that requires memory if you want to expand it first. So you prefer to do it step by step. And there is another thing that we figured out, and it was very interesting. The paper got rejected though. So I started thinking instead, do I need to rephrase it and convince my audiences that it appears that if this one is a vector and this one is a vector, this is a low rank structure. Sum of a multiplication of two vectors. Right? Sum of a multiplication to two vectors is a low rank structure. You modify that to a Kronecker product sum, pretty much whatever the composition you know of can be represented in this form. So it's also mathematically interesting that if you're thinking in a way to generalize the low rank structure of matrices, the Kronecker product is the way to go. And that actually supports more that perhaps if there is a new hardware to support a certain multiplication, they must support mostly the Kronecker product. And there is another part that perhaps comes from my statistical background, saying that how we can bring a certain matrix multiplication to lower bit number formats. Here is like WX, W hat X is a lower bit version of the W. And people usually try to see the precision to be the same. So the precision means that the matrix product are close. We just try to do it in a way that the matrix product is closed. But we want to do it in a way that the distribution function, the distribution of the weight matrix also are similar. This is the weight for the full precision. This is of the lower bit version. If you start writing that up, you figured out later that this KL divergence is bounded by this thing. And this thing, we call it the adaptive lasso. If you have this W, if we have this only the parameters that we are going to estimate that kind of goal, we call this lasso, and this is adaptive lasso. So matching the distribution of something in a higher precision and lower precision actually means the adaptive lasso sort of regularization imposed. So what will be the message at the end for this talk? Large language models, humans are different from animals because they have language. So it's not surprising that the intelligence somehow must be mimicked from the language first. Animals also have intelligence, but they have a certain language as well. So language is building blocks of intelligence. So that's the first thing. The second thing is that it's not surprising to see that computers must put translation and language in priority tasks because computers were not developed to compute. From the beginning, they were developed to translate. And I was surprised to figure this out. Okay, so the first computer called machine translator. It was not a computer. They're built to translate. It happens that since the history of computers and the history of intelligence right now is getting together, and we need to understand if we want to contribute to the future technology, somehow we need to spend some time on these language models or something that's related to them. And I encourage that more people who actually don't believe in it come to this more, because they figure out things that these computer scientists wouldn't be able to figure out. I'm done. Right, Tom?